So in this video, we are going to do some exercises based on whatever you have learned about the series convergence. And please recall all the tests that you have learned. You are free to choose the appropriate method to attack each of the problem given here. And let's start with the first problem. So you see for the first problem, the best test that we can use is actually the M-term divergence test, because you can just simply take the limit of the term you have. Then you can see that because we are taking limit n goes to infinity, we can just keep the highest power term, and the n can be cancelled as a common factor, which means the limit is actually the same as 7 over 11. And the criterion for the n-term test is that whenever the limit is non-zero, we understand that the infinite series is actually divergent. Conceptually, it's kind of like when n is big, you keep adding terms. Every term now looks like 7 over 11 because you're adding infinitely many copies of such a non-zero constant. We understand that it should diverge to infinity in that case, right? And let's look at the second problem. So in case you are very confused, you don't know what you need to do here, the fact is that I can give you some hint. Whenever you have something like the base is a constant to the power n, you see, you have the base which is 2 to the power 2n. When you see something like this, it is actually a geometric series, or the other way, you can actually write whatever you have here. So if you write it down, the infinite series, you can just expand the first couple of terms. So I'm just writing maybe at least the first 3 terms we have. So you see, in this case, I hope you can notice that there's a fixed ratio among the terms. So the fixed ratio is 2 squared divided by 3. I hope you can see that. It's simply because of the fact that you see power n is increasing one by one. You see 1, 2, 3. It means you have to multiply by the factor 3 to the bottom, the denominator. And the top is the power 2n. It means the power is increasing like 2, 4, 6, and so on. So you are multiplying by 2 squared at the top. Anyway, as a multiplicative factor, it is fixed, which is 4 over 3, basically. So let me write it down here. Basically, it is geometric, and the ratio is actually 2 squared over 3, which is 4 over 3. And by the geometric test criterion, we understand that whenever the ratio is bigger than 1, our series is actually divergent, right? So that's the answer to the problem 2. And let's look at more problem. Please look at the current problem now. It is definitely not a geometric series. If you use the M-term test, it's not going to work out. Basically, if you take the limits of the terms, you can try it yourself. It is actually 0, which means no conclusion by the M-term test. And please recall the fact that I'm trying to do it by tracing all the methods we have learned. And for those of you who are very experienced for such type of problems, you can easily spot out the correct test. But if you cannot spot it out, you can try all the methods starting from the first method you learned, right? And the next method, the P series, of course, it is not a P series. I think integral test probably works if you are good at integration, but we try to save some time on the hard integral. Let's drop it. I think actually this one, all the terms are positive. And also we can use the limit version of the comparison test to compare the current term with something greatly simplified. For example, let's take n goes to infinity for the current term we have. So you see, if you take n goes to infinity for our term here, because it is a rational function in n, and when n goes to infinity, we can just keep the dominating term with the highest degree. And we can cancel n squared, top and bottom. So it is left with the term 1 over n squared, right? And comparison test means now you see the right side is a fraction which is greatly simplified comparing to the original fraction given here. So we can just look at the infinite series formed by the simplified fraction 1 over n squared. And I trust that you can find this answer because by the P series test, now this one actually looks like P series. When the P is 2, which is bigger than 1, we understand that this infinite series is actually convergent. And by the comparison test, basically it means that our current series, which means our problem is all following the same behavior. as the infinite series with the simplified fraction. So that's the power of the comparison test. And let's look at the next problem. So that was the given series in problem number 4. And the fact is that, you see, this one is actually a sign change term. So I think it's a very good indication which test you can use. Sign change term means not all terms are positive now. It actually looks like maybe something like minus plus minus plus when you put in the terms you have. So it is definitely an alternating series. So we can directly try the alternating series test. There are two conditions to check. For the first condition, you have to take the limit n goes to infinity for the terms you have here, which is 1 over ln of n plus 1. And conceptually, it is the same as 1 over ln of infinity, and we understand that ln of infinity conceptually is the same as 1 over infinity, which is 0 conceptually. So the first condition is fine. The second condition means you have to look at the current sequence. So do you think the sequence is actually decreasing? The answer is yes, it must be a decreasing sequence because of the fact that the top is fixed, but the bottom keeps increasing. You see, the bottom keeps increasing, ln 2, ln 3, ln 4, and etc. So as a sequence, this one is actually decreasing, you see. So you see both concepts are satisfied. So by the alternating series test, we understand that it's actually convergent. That's the answer to the problem number 4. And let's go to problem number 5 now. So that was the given series, and we noticed that all terms are positive, and the important thing is about the n factorial. And this term is strange. I mean, with this term with you, and I think it's hard to do an integration. So it's not integral test. Of course, it is not geometric. You can check it yourself. And it is definitely not a P series. Of course, it is not an alternating series test, right? So we are not having that many methods with us. You can try to use a comparison test if you are good at some estimates, but it is more advanced if you use the comparison test. And it is my general hint, whenever you see the factorial term like the current case, we can actually use the ratio test. Because the ratio test is very effective in canceling the factorial, because we can take a look here. When you look at this ratio, the bottom is having the same fraction as we have here, and the top is a n plus 1 term, which means replace wherever you have the n by n plus 1, you see. So we have to do some cancellation on this fraction. So let me copy the fraction at the top, and it is multiplied to the fraction in the bottom after flipping it. So it's n factorial divided by 3 to the power n. And now you can see that you can actually cancel 3 to the power n with the top n copies. So you're basically left with only one copy of 3. And this one, n factorial divided by n plus 1 factorial. Please notice that by the definition of factorial, the top now has n factors. However, the bottom actually has one factor extra, which is the larger integer n plus 1. So we can cancel all the n common factors. So it means that this cancellation is like I am having the integer n plus 1 in the bottom. So it means we are left with the fraction 3 over n plus 1. And by the ratio test, you have to take the limit n goes to infinity for the fraction you have here. And it is quite clear that conceptually it is 3 divided by infinity, which is actually 0, right? And the ratio test means whenever the ratio is less than 1, we understand that our series is actually convergent. And that's the answer to this problem. And let's look at the last one. So please look at the current problem. I think we can actually use the integral test because we can observe that this integral can be done by this of the u substitution. I can let u be 1 over x. In that case, the u is the derivative of 1 over x, which is minus 1 over x squared, right? And I hope you can notice why it works. So if you try to transform all the things from x to u, the top becomes e to the power u, right? And you see, you are left with this term. This term is basically 1 over x squared times dx, which is exactly the same as this term. It means that we have to multiply to minus du, because minus du is the same as the remaining term we have not dealt with, right? And let me there is it times minus du because of this. And the minus can be pulled out. Basically, you are integrating e to the power u, and of course, the function is unchanged. And the u is basically 1 over x. So let me replace here. And it means I can come back to our current definite integral. And let me do it in the following line. Please look at what we have here after writing the steps down. You see the first term is conceptually replace x by infinity. And the second term will replace x by 1. I'm using some informal language here, right? Because I just conceptually replace it by infinity here. And please notice, this power now is conceptually the same as e to the power 0, which means as a concept, this first term is actually the same as 1, right? Because e to the power 0 is 1. And of course, the second term has no problem. It is just a constant. It's like minus e, right? So it means altogether, it is like the answer is something like this. You see minus open bracket 1 minus e close brackets. And obviously it is a fixed number, right? It means as an integral, it is a convergent integral. And it means that by the integral test, we understand that the series given is actually convergent. And that's the end to this problem. Actually, there's another way to deal with this problem. So you see, the second way to attack this problem is to try to understand what we have in the infinite series here. So for example, you can write the first term like this, the second term is like this, etc. You see, the fact is that you can keep a look at the top, which is the numerator. What you have at the top is a sequence of number like this, right? And you can notice that this is actually a decreasing sequence because of the fact that the power itself decreasing. And the exponential function is a monotonic function which is always increasing. So when the power keeps decreasing, we understand that the value of this term is actually decreasing every time you go to the next term for the numerator. So it means what? It means out of all the terms here, because this is a decreasing sequence, the biggest number is the first term, right? Because after the first term, everything is just smaller and smaller gradually. It means that the current series given is actually less than the infinite series with the top replaced by a constant, which is this, e to the power 1. And I think it is a very good series to deal with because e to the power 1 is just e, which is a constant itself. So I can pull it out as a common factor to all the terms inside the summation. And we understand that we can use a p series to attack this problem because p is 2 for the p series like this. And we understand the p series so well. When the p is bigger than 1, the series is actually convergent, right? And I hope you notice what I'm doing here. You see, the point is that now all the terms are positive, of course. That's the first part. The second part is the bigger infinite series is actually convergent. And when it happens like this, the bigger infinite sum is convergent, and we want to know what's happening to the smaller one, you see. By the comparison test, it must be convergent. And we have done it actually in the version 2 of the comparison test. And let me write it down here. So you see, instead of using the integral test, which is of course okay, and we can actually solve it by using a comparison test. We just have to compare it with something bigger. And this bigger one is actually a convergent series. And that's the end of this video.